Consider this circular shaft restrained at one end and subjected to a torque about its axis, while a fibre from this shaft distorts as follows, and this angle of distortion is the shear strain. And consider a cross section that's at a distance z from the origin, then this arc length is gamma multiplied by z, which is this length over here. And this angle here is called the angle of twist, which is denoted by phi. And this arc length is therefore also equal to r multiplied by the angle of twist. So gamma is constant at every cross section, and so is the radius of the shaft. So we can write this in differential form as r by d phi, which is equal to gamma by dz, where d phi is the change in the angle of twist between two sections. So this here is phi plus d phi for a section that's at z plus dz from the origin. Now recall the torsion formula, where the shear stress is equal to the torque by the distance r from the center of the shaft on the polar moment of inertia, which is a moment of inertia about the z-axis, which is izz. And the shear stress is related to the shear strain by the shear modulus. So therefore the shear strain is mz by r on the shear modulus by the polar moment of inertia, which we can substitute into this relation. And now if we cancel r and integrate both sides, and we integrate from an angle of twist of 0 where the bar is restrained to an angle of twist phi at some distance z from the origin. So this gives the following relation for the angle of twist. So we have mz multiplied by z over the shear modulus by the polar moment of inertia. So note that the angle of twist does not depend on a radial distance from the center of the shaft. So at a distance of z equals l, which is the length of the shaft from the origin, we get the angle of twist is mz by l on gizz. Now let's go back to the general form. So therefore the rate of twist is equal to mz on the shear modulus by the polar moment of inertia. And we'll use this to derive the torsion equations for beams which do not have a circular cross section.